Welcome back to Mining of Massive Datasets. We continue our discussion of clustering by looking at hierarchical clustering methods. To refresh our memory, in hierarchical clustering, we can either go bottom-up or top-down. In bottom-up methods, each data point is initially in a cluster of its own. At each step, we find the two closest clusters and combine them into a single cluster. In divisive methods, all the data points are in a single cluster to begin with, and we recursively split the cluster as we go along. In this lecture, we're going to focus on the agglomerative or bottom-up approach, where we start with each data point as its own cluster and then combine clusters. The ideas in the lecture can be easily adapted to divisive methods as well. The key operation in hierarchical agglomerative clustering is to repeatedly combine the two nearest clusters into a larger cluster. There are three key questions that we have to answer in order to build a hierarchical clustering algorithm. Those three important questions are the following. How do you represent a cluster of more than one data point? We need a representation of a cluster so that we can figure out which clusters are close to each other. And that brings us to the second question, which is how do you determine the nearness of cluster so that we can combine the two nearest clusters? And the third question is, as we keep going along and combining clusters, when do you decide to stop and produce a final output? So we'll look at each of these three questions in turn. Let's start with the simpler case of a Euclidean space. In a Euclidean space, we can always average 2 points, and the average is also a point in the Euclidean space. This gives us a simple answer to the question of how do you represent a cluster of many points. We can represent a cluster by its centroid, which is the average of its points. And to determine the nearness of clusters, we just measure the cluster distances by measuring the distances between the centroids of the clusters. An example will make this clear. Here we have 6 points in a Euclidean space. These O's represent data points in a Euclidean space, and we're going to apply an agglomerative clustering methods. Initially, let's say we determine that these points 1, 2, and 2, 1 are the closest points. We combine them into a single cluster, and now we're going to represent this cluster by its centroid. To compute its centroid, we have to compute the average of the 2 points, which is just the average along every dimension. So the average of the points 1, 2, and 2, 1 is the point 1.5, 1.5, which is the centroid of this newly created cluster. Now we have 5 clusters. Remember, we started out with each data point as its own cluster, and we've combined 2 of the data points into a single cluster. So now we have 5 clusters. Now we need to find the nearest pair of clusters. And as it turns out, the nearest pair of clusters is the pair of points 4, 1, and 5, 0. And once we've created this cluster, we then represent it by its centroid. Now the centroid of this cluster is the point 4.5, 0.5. Now the 4.5 is obtained just by averaging the x coordinates of the 2 points, and the 0.5 is obtained by averaging the y coordinates, which are 1 and 0. So now we have 4 clusters. Okay? And as we go along merging clusters, we create this artifact called a dendrogram. And the dendrogram shows how we merge data points and clusters as we go along. In the first step, we merge the 2 blue data points, and in the second step, we merge the 2 green data points, and that's what the dendrogram indicates. Now in the next step, we determine that the 2 closest clusters are the cluster with centroid 0, 0 and the cluster with centroid 1.5, 1.5. And we can measure, we do this just by measuring the distance between 0, 0 and 1.5, 1.5, and finding that to be the shortest distance between any pair of clusters. Once we do that, we can combine the 3 points 1, 2, 2, 1, and 0, 0 into a single cluster, and we can represent it by its centroid, which is 1, 1. Now to determine the centroid of this combined cluster, we have to average all 3 points 1, 2, 2, 1, and 0, 0. and the average in the x, in the x axis is 0 plus 1 plus 2, which is 3 divided by 3, and that gives you 1, and similarly along the y-axis. So now we have 3 clusters, one cluster with centroid 1, 1, another with centroid 5, 3, and a third with centroid 4.5, 0.5. And when we measure the intercluster distances between these 3 centroids, we determine that the two closest are 5, 3 and 4.5, 0.5. So we can combine those, and that new cluster has centroid 4.7, 1.3. Now we are reduced to 2 clusters, and we have no choice at this point but to merge these 2 clusters. So either we can stop at this point and output these 2 clusters, or we can decide to merge them further and create a single large cluster. And now a single cluster doesn't make a lot of sense, because our goal was to end up with group the points into many different clusters. But on the other hand, even if we do merge these 2 clusters and create a single large cluster, the dendrogram actually shows the order in which these the merges happen, and it contains very useful information in many cases. For example, if the data points actually represent species of different animals, then the dendrogram represents a family tree of how these species evolved. Now that was the easy or Euclidean case of hierarchical agglomerative clustering. But what if we have a non-Euclidean space? The problem with a non-Euclidean space is that it's not possible to average points and create a centroid. The centroid may not be a valid point in the non-Euclidean space. So the only points or locations we can talk about in a non-Euclidean space are the points themselves. There is no concept of average. And therefore, we cannot continue using the centroid to represent a cluster. So instead, we have to use a different concept called a clusteroid. And a clusteroid is a data point that's closest to the other point in the cluster. So once we use clusteroids instead of centroids, and we look at an example of clusteroids in the next slide, we can determine the nearness of clusters by treating the clusteroid exactly as if it were the centroid. And we can measure the distance between 2 clusters by measuring the distance between their clusteroids instead of measuring the distance between their centroids. Here's a cluster on 3 data points in a Euclidean space. Now, the centroid, which we saw how to compute, is just the average of all these data points in the cluster. The X here marks the centroid of the 3 data points shown. Notice that the X is actually a data point that was not among the original 3 data points in the cluster. It's an artificial point that we created to represent the cluster. Now, the problem in non-Euclidean spaces is that we cannot create this artificial point, and therefore, we just have to pick one of these 3 points as a clusteroid to represent the cluster instead of using X, the centroid. So in this case, for example, we might pick the point shown as a clusteroid to represent the cluster, because intuitively it's in the middle of the cluster and it's close, and it sort of seems to be equidistant from the other points, and therefore we might pick the highlighted point as a clusteroid. And notice that the clusteroid is actually an existing data point. It's not the centroid, but for all practical purposes, we can treat it as a centroid in clustering algorithms. Now we've defined the clusteroid to be the point that is closest to the other points within the cluster. Now, how exactly do we define this notion of closest point? It turns out that there are multiple ways of defining the notion of closest when we are picking the clusteroid. For example, we might want to pick the point that is at the smallest maximum distance to other points, by which we mean we measure the distance between every pair of points, and then we find a point such that the maximum distance between that point and any other point in the cluster is as small as possible. Instead, we might look at the point with the smallest average distance to the other points. Or we might look at the point with the smallest sum of squares distance to other points and pick that as a clusteroid. Depending on the application, one or the other of these notions of clusteroid might make more sense than the others. So far, we've addressed the first 2 of the 3 key questions of clustering. The first being, how do you represent a cluster, and the second being how do you determine the distance between clusters. We now turn to point 3, or the termination condition. How do you know when to stop clustering and produce an output? The first approach is to pick a number k up front and stop when we have k clusters. Now this approach makes sense when we know upfront that the data falls naturally into k classes. For example, the data might be about galaxies and quasars, and we know that there are naturally two classes, galaxy and quasar, and once we have two clusters, we stop. The second approach, when we don't know the number k up front, is to keep clustering and stop when the next merge of clusters would create a bad cluster. Now, how do we define a bad cluster? We define a notion called cohesion, which measures the goodness of a cluster. And when the cohesion value falls below a certain level, we've created a bad cluster. And we stop when the next merge would create a bad cluster. How exactly do we define this notion of cohesion? There are multiple approaches to defining cohesion. The first approach to cohesion is to use the diameter of the merge cluster. Now, the diameter of the merge cluster is the maximum distance between any pair of points in the cluster. We might decide to stop clustering when the diameter of a newly merged cluster exceeds a certain preset threshold. The second approach is to use radius. The radius is the maximum distance of a point from the centroid or the clusteroid. And we might decide to stop clustering when we would produce a cluster of greater than a certain threshold radius. The third approach is to use a density-based model. Now, density of a cluster is the number of points per unit volume of the cluster. One way of defining density is to simply divide the number of points in the cluster by the diameter or the radius of the cluster. We might instead divide the number of points by a power of the radius, such as a square or a cube. And at a point where the next merge would create a cluster with a density lower than a certain preset threshold, we'd stop merging and produce a final output. Notice that in each case, we set a predefined threshold either for diameter, radius, or density, and stop when the next merge would violate that threshold. We turn now to implementation of hierarchical agglomerative clustering. At each step in hierarchical clustering, we need to find the closest pair of clusters and merge them. In order to find the closest pair of clusters, we need to compute pairwise distances between all pairs of clusters. Since we start with each point in its own cluster initially, there are order n clusters where n is the number of points, and therefore computing pairwise distances takes time order n squared. Overall, we might have to do order n steps of merging, and therefore the overall complexity of hierarchical agglomerative clustering is order n cubed. Now, if we do a careful implementation using priority queues, we can reduce the complexity to order n squared log n. N squared log n, though, is still too much for really big data sets that don't fit in memory. When n is of the order of millions, order n squared log n can get out of hand pretty soon. That's why hierarchical clustering is not commonly used for really big data sets that don't fit in memory. It's primarily used for small data sets that do fit in memory. When you have really large disk resident data sets, we use other methods of clustering, which we turn to next.